Hello everyone, welcome to the YouTube channel of YourPedia and Engineering Career Point. So I am Vinny Sharma, your mentor of mechanical engineering. So as you know, we have launched the module of BEL, BDL as well as the BHEL. Okay, and all of these modules are combined here. So and the expected date of the exam for the BDL exam is around 15th of March, and after that we have around 1 month, or I can say 20 to 25 days for the BHEL exam. Okay, so now right now we are covering the theoretical portion that is important for the BEL exam as well as the BDL exam, and after the BDL exam we are going to specifically focus on the BHEL part. We are going to cover all the numerical portions of every subject. Okay, so now in this video basically I am going to provide you the previous year solutions of the BHEL paper, and now you are going to see that in this exam paper we are going to have a very large number of numericals here. Okay, so before any delay here, so let us start our solutions part. So now just read out the first question here. So this is the first question, and one more thing, this question paper is basically is held on the 2023 here. Okay, so that is the solutions of the exam 2023 which is conducted by the BHEL. So now in the first question, what is given to us? A heat engine receives the heat from a source of 1200 Kelvin at a rate of 400 kilowatt and rejects the waste heat to a medium at 300 Kelvin here. Now the power output of the heat engine is around 160 kilowatt, and what will be the irreversibility rate you have to calculate here. Okay, so now just see, here we have been provided that a heat engine is operating between the two temperature reservoir, that is 1200 Kelvin and the 300 Kelvin here, and the corresponding work output from the one engine is actual heat engine is 160 kilowatt. So we can say the actual availability, the actual amount of work done, or we can say the actual availability from the engine is basically equal to 160 kilowatt here. Okay, but now if you want to find out the maximum amount of availability which is there in the 400 kilowatt of energy, so you can also calculate it here. So here you can see the maximum availability will be calculated as Q multiplied by 1 minus lower by higher temperature. Okay, so that is basically representing the maximum amount of work done which you can extract if the heat engine is Carnot engine. So if you put all the values into this expression, you will get your final answer. So here we can say the value of the maximum availability is coming out to be around 1 by 4, that is 300 kilowatt. Okay, and the irreversibility rate, see, the decrease in available energy, the increase in unavailable energy, and the irreversibility all are the same thing here. Okay, so if you want to find out the value of the increase in unavailable energy or decrease in available energy or the irreversibility rate, it can simply be calculated by taking the difference of maximum availability minus the actual availability. So we can say irreversibility rate is nothing but it is a difference of 300 minus 160 kilowatt here. The answer will come out to be as 140 kilowatt here. Okay, so the option number C is going to be the correct answer of this part here, 140 kilowatt here. So that is a very simple part. Okay, but you should have a basic understanding that how do we calculate the availability for different cases here. Okay, so see the next question here. So next question is, an idle gas is stored in a closed tank of volume V. So here we have a, let us say here we have a let me draw a diagram here. So let us say here we have a container whose volume is given to you as V here. Okay, and absolute temperature of T0 and pressure P here. So here in this case the temperature of an idle gas is T0 and pressure is P here, and we have to ignore the effect of motion as well as gravity, and we have to calculate that what will be the specific energy, that means the availability per unit mass of a air here in that case. And you have also been provided with the environmental conditions, that is T0, P0 as well as gas constant R here. Okay, so now just see how do you calculate the availability. See, there are very different methods to calculate the availability for the case of open system as well as for the closed system. So when we talk about the closed system, in that case the availability or the specific energy can be calculated as U minus U0 minus T0 S minus S0 here plus P V minus V0 here. Okay, so the notations with the O subscript is representing the environmental conditions here. Okay, so now here you can see the environmental temperature is T naught, and along with that the temperature of the air inside the container is also T naught. So we can say the change in internal energy U and U naught is going to be 0 here. Why so? Because for an ideal gas the internal energy is a function of temperature only. Okay, so now you can see, now the temperature T and T naught are same, therefore I can write U is going to be equal to U naught here. Okay, so therefore I can say that the availability is nothing but it is equal to P naught V minus V naught minus T naught S minus S naught here. Now how do you calculate the availability here? So now just see one more thing. Here in this case, all the options doesn't contain any terms in volume here. Okay, so we have to convert this volume in terms of pressure, volume, pressure, characteristic gas constant, and temperature here. So here you can see the volume V of the container can be written as RT naught divided by pressure, and V naught can be written as RT naught divided by P naught here. And S minus S naught is representing the change in the entropy of an ideal gas, okay, at the inlet condition as well as at the atmospheric condition. So we can say the entropy change can be written as Cp ln of T naught by T naught here, because the temperature inside the container and the temperature outside the container are same here. Okay, minus R ln of P by P naught here. Okay, so now here you can see, the inside pressure is P and the outside pressure is P naught here. Okay, so we can say the availability is going to be here. Okay, the first term it is going to be 0 because the value of the natural log 1 is coming out to be 0 here. So we can say the availability can be written as RT naught P naught upon P minus 1 plus RT naught ln of P by P naught here. Okay, so if you simplify it further, you will get your final answer as the value of the specific energy. So value of the specific energy will become RT naught P naught by P1 minus 1 plus ln of P by P naught here. Okay, so this is coming out to be the specific energy here. Okay, so here you can see the option number C is going to be the correct answer of this part here. Okay, so here you can see you have to do the entire exact derivation to find out the final answer here. Okay, so that is a very important part. Now the next part is, which of the following statement is incorrect? You have to mark the incorrect statement in case of the assumption made while during the derivation of logarithmic mean temperature distribution. Logarithmic mean temperature difference here. So where do you use the LMTD here? LMTD concept is used in the case of heat exchanger, which you study in the heat transfer subject. So now just see, whenever you are calculating the value of the LMTD, there are certain assumptions you have taken here. The first assumption that the overall heat transfer is constant, that is correct here. Okay, option number A is perfectly correct. Next, there is no change of phase of the fluid during the heat transfer, that is also correct here, because if you see while formulating the formula of the LMTD as well as the AMTD, you haven't considered the latent heat here, latent heat transformation here, or you can say you haven't considered the phase change process here. Okay, so here you are saying that the temperature of the hot fluid is continuously decreasing and the temperature of the cold fluid is continuously increasing here, okay, while flowing through the heat exchanger. Now the next part is specific heat of both the fluids are constant, that is also correct here, because in the case of heat exchanger we always assume that the specific heat is not a function of temperature there, it is having a constant values for the hot fluid as well, as for the cold fluid also. Next part, the flow condition are unsteady, that is incorrect here, because whenever you are studying any device which is find its application in industries, there we always assume that the flow conditions are always steady here. Okay, so the option number D are going to be the correct incorrect answer here. So we can say the answer of this question is option number D here. The next part is transmissivity versus the frequency ratio curve. for the various values of the damping factor is shown in the figure here. Which of the following is the correct here? So you have to know that what is this graph is representing here, and this graph is always shown between the transmissibility as well as the frequency ratio. Now what is the meaning of transmissibility here? Transmissibility is defined as the ratio of the force transmitted to the foundation here, okay, which is being produced by the machine here. Okay, so whenever you are installing the machine over a structure, you have to make ensure that there is some vibrating isolating material present between the machine and the foundation here, so that we can reduce the transmission of the forces from the machine to the foundation here. Okay, so now what is this graph is representing here? For all the values of damping factor zeta, the transmitted force is always greater than exciting force when the frequency ratio is greater than √2. So here you can see there are some observation here. So here we have a value of frequency ratio as √2, and corresponding to √2, the value of the transmissibility is going to be 1 here. Okay, so that means if the value of the frequency ratio, that is omega by omega n, is equal to √2, we can say the corresponding value of the transmissibility is going to be equal to 1. So okay, now what is the meaning of that? It simply means the amount of forces which are being produced by the machine is every force is going to be transmitted to the foundation here. The same amount of force which is produced by the machine is going to be transmitted to the foundation here. And if you go below the toward the left side of the frequency ratio, here you will find that the value of the transmissibility is going to be more than 1 here. Okay, so here you can see if the value of the zeta is equal to 1, the transmitted force will become equal to infinite here. Okay, or I can say its value is going to be very, very large here. So as you are increasing the value of zeta, or we can say as you are increasing the damping inside the system, the corresponding value of the transmitted force is continuously decreasing here. Okay, but now if you see above the value of frequency ratio √2, if the value of the frequency ratio is more than √2, in that case, no matter what you do, or the transmitted force is always going to have a less value as compared to the excited force here. Okay, because here the value of the transmissibility is always going to be less here. Okay, and also there is one more thing, that if you increase the value of the damping, if you increase the value of the zeta after the frequency ratio is more than √2, then the corresponding transmitted force will increase here. Okay, why so? Because here you can see this value is having a value of zeta of around 1.0. This value of this graph has a value of zeta around 0.6 here. Okay, and similarly the bottom graph is going to have a value of the zeta as 0 here. Okay, so that these are some of the important conclusions which you can derive from this particular graph here. So we can say for all the values of the damping factor zeta, transmitted force is always less than the exciting force when the frequency ratio is less than √2. That is incorrect. Option number A is incorrect. For all the values of damping factor zeta, transmitted force is always equal to the exciting force when the frequency ratio is greater than √2. That is also incorrect. Okay, because the transmitted force is always going to be equal to the exciting force when the frequency ratio is equal to √2, not the greater than √2 here. Next part, for all the values of the damping factor zeta, the transmitted force is always less than the exciting force when the frequency ratio is greater than √2 here. That is the correct statement here. Okay, so option number D will be the correct answer of this particular question. Now the next part is, a block of wood specific gravity 0.9 is floating at the interface between a layer of gasoline and a layer of water, as shown in the figure here. So now what do you want to find out? What fraction of the wood block is below the interface if the specific gravity of gasoline is 0.74 and that of water is 1 here. So here you can see, let us suppose if the total volume of this block is V here, and here I am assuming the volume which is present inside the water is represented by VW here. Okay, and the volume of block which is present inside the gasoline is represented by Vg here. So I can simply say that the value of V is going to be equal to sum of VW as well as the Vg here. Now what do you want to find out? You want to find out what fraction of the wood block is below the interface. That means you have to find out the value of Vw divided by V here. Okay, you have to find out this value of X here. So how do you calculate this value? So first of all, if you know the Archimedes principle, so here you can see the total weight of the block is going to be equal to the total point force which is acting on the block here. Okay, so we can say the weight of the block is going to be equal to the sum of buoyant forces here, and the weight of the block can simply be calculated as the mass into gravity here. Okay, so we can say the mass into gravity will be 960, that is will be the density, multiplied by gravity multiplied by total volume. So this is representing the total weight of the block, and correspondingly FB1 can be written as FB1. Let us suppose FB1 is representing the buoyant force which is acting due to the water here, okay, on the wooden block, and FB2 is representing the buoyant force which is acting by the gasoline on the wooden block here. So we can write the buoyant force FB1 can be written as rho W gravity multiplied by VW plus rho gasoline gravity V gasoline here. Okay, so if you simplify it further, you will find that 960 is going to be equal to 1000 multiplied by X plus density of the gasoline is given to you as 740 multiplied by 1 minus X here. Okay, so that is that expression you are going to get here. So you have to calculate this value of X here. So we can say the value will come out to be around 960 minus 740. It is going to be equal to 1000x minus 740x here. So if you solve this, you will find out the value of x, and it will come out to be around 220 divided by 260 here. Okay, so you can find out the exact value of the x here. So exact value it will be come out to be around 0 point something, like I think it is coming out to be around 0.24 here. And if you mark the options here, the option number C will get the almost very close answer here. Okay, the 5 by 6 is around 0.833 here. Okay, so here the option number C is very close to this value here, 0.884. So we can say the option number C can be the correct answer. Okay, even though it is not a correct answer, but it is very close here. The next part is, which of the following is correct for the gear? Here A is representing the circular pitch, C is representing the module, and the B is representing the diametrical pitch here. So here you can see A is nothing but is equal to pi d upon t, and the d by t is called as the module here. So we can say A is equal to pi into C here. The next part is diametrical pitch. Now what is the meaning of diametrical pitch? Diametrical pitch is represented by B here, and it is defined as the ratio of number of teeth divided by pitch circle diameter here. So we can say it is a reciprocal of module. So therefore we can define the BC is going to be equal to 1 here. Okay, so the option number A is going to be the correct answer of this question here. Next part, a wheel is rotating about its axis with an angular acceleration at time t, which is given by this particular expression here. Now when the t is equal to 0, the position is taken as 0 and its angular velocity is 5 radian per second here. So initially at time equal to 0, we have a angular velocity of 5 radian per second here. Okay, and now you have to find out what would be the angular velocity at time t equal to 10 seconds. So here you can see, as you are increasing the time, so now the angular acceleration is given by this particular expression. So we can say the angular velocity can be written as omega 2 equal to omega 1 plus alpha dt here, and the integration you have to perform from 0 to 10 here. Okay, because we have to calculate the value of the angular velocity at t is equal to 10 second here. So in that case, if you just put out all these values here, you can see the omega 2 will come out to be around 5 plus 6 by 3 10 cube minus 0 plus 2 10 minus 0 here. So the answer will come out to be around 5 plus 2000 plus 20 here. Therefore omega 2 will become 2025 radian per second here. Okay, so the option number B will be the correct answer of this particular question here. Okay, the next part is, if the refrigerator unit having a mass of 44 kg is to be supported on a 3 springs here. So now we have a refrigerator which is supported on 3 springs here. Here we have 3 springs. Okay, so here you can see. Now if the unit operates at 450 rpm, and correspondingly you have to find out the value of the stiffness if only 10% of the shaking force is allowed to be transmitted to the supporting structure here. So we can say here the value of the transmissibility, that is the Ft by F ratio, is given to you as 0.10 here. Okay, and one more thing, the value of the mass is provided to you. So we don't have any stiffness here, sorry, we don't have any damper here, so we can say the value of the C is going to be 0, the correspondingly zeta is going to be 0 here. And here the 3 springs are in parallel connection with each other, so we can say the K equivalent is going to be equal to 3 times K here. Okay, because in the case of series connection, because in the case of parallel connection of the spring, the equivalent stiffness can be calculated by simply summation of all the stiffnesses here. And the next part is, now the machine is operating at 450 rpm. So if the machine is operating at a speed of 450 rpm, so we can say the omega is going to be equal to 2 pi 450 divided by 60. Okay, and that will come out to be as it is coming out to be as 30 pi, I think. So sorry, it is coming out to be as 15 pi here, 15 pi here. Okay, the omega is coming out to be around 15 pi. So now here you can see the value of the zeta is equal to 0. Then the formula of the transmissibility, which is a very complicated formula which is given by this particular expression, will be simplified further. Okay, so this is the formula of the transmissibility here. So in that case you can see that if the value of the zeta is going to be 0, so this term will become 0 and this term will become 0. So therefore the effectiveness transmissibility formula will become 1 minus 1 minus 1 divided by 1 minus omega by omega n whole of square. Okay, so this will be the formula of the effectiveness. So here you can see the value of the omega by omega n square is going to be equal to 1 upon transmissibility plus 1 here. So it will come out to be around 11, and from here you can calculate the value of omega n. Okay, so we can say the here I can say write 15 pi square divided by omega n square. It is going to be equal to 11, and from here I can define K effectiveness divided by m is going to be equal to 15 pi square divided by 11 here. Okay, so here you can see the value of the K effectiveness is nothing but it is equal to 3K. So I can write 3K divided by 44 is going to be equal to 15 pi square divided by 15 here. Okay, so if you solve this, you will get the value of the stiffness of the spring around 2960 Newton per meter here. Okay, so that this value is very close to 2.96 Newton per millimeter, or we can say 3 Newton per millimeter here. So here the option number C will be the correct answer of this part here. Okay, so here you can see you have to do the exact that mathematical calculation for solving this question here. The next part, and one more thing, for solving all of this part here you only have 35 to 40 seconds here. So you have to make sure that you have that you revise your questions very properly, you revise your formula, all the formulas very carefully here. The next part is the spectral distribution of the space irradiation is shown in the figure. What will be the irradiation of the surface? Now here in the case of radiation part, we normally study two type of terms here. The first one is the irradiation and the second one is known as the radiosity. Now what is the meaning of irradiation? Irradiation basically represents the total amount of heat transfer, total amount of radiation which are acting on the, which are striking on the surface here, and the radiosity is representing the total amount of radiation which are leaving from the surface here. Okay, so now in that case we have been provided with the spectral distribution of surface irradiation, with the wavelength here. So here if you want to find out the value of the total irradiation, so that is a very simple part. The total irradiation can be calculated by calculating the total area here. Okay, so here you can see the area of this triangle is, now the value is not visible to you, it is around 1000 here. Okay, and it is around 5, 10, 15, 20 and 25 here. So you can see the area of the first triangle will be half 1000 multiplied by 5 here, and the area of the middle triangle will be 1000 multiplied by 20 minus 15 here, 20 minus 5 here, and the area of this second triangle is around this one here. Okay, so if you solve the entire this expression, you will find your answer 25 plus 25 5000 plus the middle one will be 15,000. So we can say the irradiation is coming out to be around 20,000 watt per meter square here. Okay, so here the option number C is going to be the correct answer. Okay, so that is a very simple part. Now the next part is a plain composite wall C figure. Cross sectional area is given to you as 1 meter square. One layer is made up of material A, which is having a thickness of 100 millimeter here. So here we have a thickness of around 100 millimeter, and the second layer is having a thickness of around 10 millimeter, and the corresponding thermal conductivities are given to you. So here the material number A is having a thermal conductivity of 15 watt per meter Kelvin, and second material is having a thermal conductivity of 2 watt per meter Kelvin here. So now what do you want to find out? So you want to find out the rate of heat flow. Okay, and see, in this question one more thing is given to you. We have a thermal contact resistance at the interface of the A and B here. So here you can see the total amount of heat transfer can simply be written as delta T upon R total here. Okay, so if you create the thermal circuit here, so you will find there will be a resistance of material A, there will be a resistance of material B, along with that we have a resistance of this contact here. Okay, so we can write that Q is going to be equal to R1 plus R2 plus R3 here, and here in this case the delta T will become 300 minus 550 divided by resistance offered by the material number A, that is the conduction resistance, can be calculated by the ratio of 100 millimeter divided by thermal conductivity. Okay, and the value of R2 is given to you as 0.003, and similarly the value of the thermal conduction resistance of the second layer will be thickness divided by conductivity. Okay, so if you solve this expression you will get your final answer, and the answer will be coming out to be around 25 kilowatt here. Just calculate it and you will get your final answer here. Okay, so option number D will be the correct answer of this part here. Next part, in the next question we have a follower which is moving with a simple harmonic motion, and its maximum acceleration you have to calculate. Okay, so this is a direct formula based question. So in that case you can write the value of the maximum velocity in the case of simple harmonic motion is pi by 2 omega s by theta naught here, and corresponding value of the maximum acceleration is around pi square omega square s upon 2 theta naught square, and similarly the maximum value of the jerk is going to be around pi cube omega cube s upon 2 theta naught cube here. Okay, and that will be having a negative sign. So in that case the maximum velocity is going to be at an angle of theta by 2. The maximum value of acceleration is going to be at 0 degree and theta naught, and correspondingly the maximum value of jerk is going to be at 0 degree and theta naught here. Okay, so you have to remember this, all of these formulas here. Along with that you have to remember that where we are getting these values here. Okay, that means the values of the angular positions. So in that case the option number A is going to be the correct answer of this part. Next part, in the compression stroke of an IC engine, the heat rejected to the cooling water is around 65 kilojoule. Along with that we have a work input of 108 kilojoule per kg, and the change in specific internal energy we have to find out. So here you can directly use the first law of thermodynamics. So you can see the heat is getting rejected from the system, that means it is a minus 65 here, and the work input is given to you, that means minus 108 is given to you. So we can say the value of the change in internal energy will come out to be around 43 kilojoule per kg here. Okay, and this value is coming out to be positive, that is representing that there will be a gain in internal energy of a 43 kilojoule per kg. Next part, a horizontal pipeline diameter 60 centimeter carries oil at the rate of 10 to the power 5 meter cube per day. The frictional head loss is given to you, which is observed as at 8.5 meter per 1000 meter here. Along with that, it is planning to place the pumping station at every 20 kilometer along the pipe here. So what will be the pressure drop between the two pumping stations? Okay, so just see one thing here. In this case, the head loss of 8.5 meter is taking place over a distance of 1000 meter here. So we can say the head loss over the 1 meter will be 8.5 divided by 1000 here. Okay, and you want to find out the value of the pressure drop. So we can say the total pressure drop will be HF multiplied by L here. Okay, so value of the rho is given to you around, okay, so in the question the value of rho g is given to you now, that is 9000, and HF is given to you as 8.5 divided by 1000 here, and you have to calculate the value of the pressure drop over a distance of 20 kilometer here. So just convert it into the SI units, that is 20,000, and if you find out the value of the delta P here, it will come out to be around 1.53 mega Newton per meter square. Okay, so this question is little bit of aptitude type. So here the option number C will be the correct answer. The next part, each arm of a Potter governor is 200 meter long and is pivoted on the axis of rotation of the governor. The radius of the rotation of the ball at minimum and maximum speed are 120 and 160 millimeter respectively. The mass of the sleeve is 25 kilogram and that of each ball is 5 kilogram here. So what will be the approximate values of maximum and the minimum speed of the governor here? So you have I have already told you that you are going to get only 35 to 40 seconds to first solve this type of questions here. Okay, so you don't have to do the complete calculations here. You just have to use your basic aptitude. So now in this case, if you remember, in the case of a Potter governor, the value of the maximum speed can be, just wait a minute, here you can write the expression, between the height and the speed in this way, 895 divided by n square 2 mg plus mg plus minus f 1 plus k divided by 2 mg here. So now in this case, upper and lower arm are pivoted on the axis of the rotation, that means the value of the k is going to be 1 here. Along with that, we don't have friction present inside the system, so we can say the formula of the h will become 895 divided by n square multiplied by small m plus capital M by small m here. Okay, so now just see, in this question we have to calculate the value of the maximum and minimum speed. So why don't we calculate the ratios here? Okay, because that will be much easier for us. So here I can say the values of the maximum speed divided by the minimum speed is going to be equal to h minimum divided by h maximum. H minimum means the height of the governor corresponding to the minimum speed of the governor here. So here we can say the n max divided by n mean is going to be under root of h mean by h max here. Okay, so now just calculate the values of h mean here. So in this case, if you see, in the Potter governor the arm are 200 millimeter long and correspondingly at the minimum speed we have a radius as 120 millimeter here. So this 120 millimeter is corresponding to the minimum speed of the governor. So here you can see this is going to represent the minimum height. Sorry, it is not a minimum height, it is a height corresponding to minimum speed here. So if you calculate the value of h mean, it will come out to be around 160 millimeter here. And similarly, the value of the h max will come out to be around 120 here. Okay, so we can say, just wait a minute, I don't have enough space right now. Okay. So if you just find out the values of h minimum by h max, you will get the x values as 160 divided by 120 here. Okay, and this value will come out to be around 1.15347 here. So just find out the values of the maximum by minimum speed in all the options here, and you will find the option number D is going to be very, very close here. So option number D will be the correct answer. Okay, you don't have to solve each and every part in this question. Just find out this ratio, okay, and compare it with the options here. That will be much easier for you. The next part, two very large parallel plates are maintained at a uniform temperature of 800 Kelvin and 640 Kelvin, and the corresponding emissivities are given to you as 0.2 and 0.5 here. And we have to calculate the values of the net rate of radiation heat transfer which is taking place between the two surfaces here. Okay, so that's a very simple part. In that case, you can simply calculate the values of the rate of heat transfer as sigma T14 minus T24 here, divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1 here. So just put all the values here. In that case, in the question itself, the values of 800 to the power 4 minus 640 to the power 4 is given to you. That is 2.4 multiplied by 10 to the power 11. (0.2), 1 divided by 0.5 and minus 1 here. Okay. So if you solve this, you will get a final answer of the rate of heat transfer between the two parallel plates as 2268 watt per meter square. Okay, so this will be the answer of the rate of heat transfer. So here you can see we have solved the first part of the BHEL previous exam here. Okay, so in this question paper you can observe that there are very large number of numericals there. Okay, in the first 15 question we have solved a very large number of numericals as compared to the theory here. Okay, so you have to be very careful while studying the preparing for this particular PSU here. Okay, you have to be very choosy with your subject here, that which subject do you want to cover. Okay, and which and from that particular subject within in how much time you will solve these questions here. Okay, so that is for today's videos here. Now we will proceed with the next part of the question paper in the next video itself. So thank you very much.